You've probably heard the effects of audio timescale modification when you've sped up or slowed down a YouTube video. And in this video I'm going to explain how a timescale modification algorithm works. I'm going to base my video on an example of Tom Hanks saying a famous line from the film Forrest Gump.
I'm pretty tired. Think I'll go home now.
Now, in order to understand the algorithm, it's best to first understand how it works from a waveform perspective. So I'm going to zoom in on a single word, I'm. And when we zoom in, we can see that the waveform has kind of a periodic structure associated with it. And timescale modification algorithms take advantage of this and basically just discard or repeat certain segments. So in this example, I've expanded the waveform and the waveform below. Basically all I've done is repeated the green parts of the waveform twice. So the red parts are basically a repetition of the green parts, and that causes timescale expansion. If I was to delete those segments, we can then get timescale compression. So you can see that the idea behind the algorithm is quite straightforward. All we're doing is discarding or repeating certain segments of the waveform, and we'll get greater expansion if we repeat more segments, and we'll get greater compression if we remove more segments. So one of the key things is to appreciate that the duration of the segment that we discard or repeat needs to be quite short. If that gets too big, well then the algorithm just sounds terrible. The other thing to be aware of when we're implementing these algorithms is that the segments that we're sticking together or removing, we need to make sure that when we join the segments together that we do it in a smooth fashion. Otherwise we're going to hear clicks and pops in the audio. So what I'm going to do next is run through some Matlab code that basically does just what we've seen. So here is the code, and I will put a link to this code in the description part of the video. It's a function that I call speech TSM. It's not that long, it's only got 54 lines in total. And it's reasonably easy to understand, and I'm going to explain how it works in a second. First thing I'm going to do though is just demonstrate the algorithm output. So we'll take in a recording of Forrest and we'll listen to him first of all. So it was sampled at a rate of 44,100.
I'm pretty tired. Think I'll go home now.
So the function speech TSM, it takes the input, the sampling rate and the timescale factor as the input parameters. So what this 0.6 means is it's going to timescale compress it or reduce the duration to 60% of the original duration. So we can set that to whatever we want. It has to be greater than 0, but it can be any number. So we can timescale to any factor we want. It sounds a bit funny after for high timescale factors. And then we can listen to the output.
I'm pretty tired. Think I'll go home now.
So you can hear that that sounds pretty good. It also only takes a moment to run that algorithm. It's very, very quick. Now what I'd like to do is just show you how the algorithm works. So I have a second version of this code which I've called speech TSM demo, and that basically just has some plotting in it to show you what's going on with the waveform, and I'll put a link to that code in the description part of the video as well. So let's apply that demo version to a short segment of the speech signal. And this corresponds to the word I'm. So what I'm going to do is just run that algorithm now. I'll use the demo version of it and I'll apply it to the segment and also make it 1.3. So this is going to timescale expand that segment to 30% longer. So it'll be 30% longer than the original duration. So this is just going to illustrate how the algorithm works. So this is my input signal. So that's the segment that you will recognize from the earlier part in the video. And the first thing that happens is that we grab a frame. So the frame are shown here as red samples, and it's basically copied to the output. So this bottom waveform is going to be is the output, and it's going to be built up gradually in an iterative process. Okay, so we grab a frame of length 2352. Now this number is determined using an equation, and the equation is dependent upon the timescale factor, the length, maximum length of segment that we can discard or repeat, and also what's called a search range, and I'll explain what the search range is in a little second. Okay, so the next stage in the algorithm will be to grab the next input frame, and the next input frame is obtained by stepping in a certain amount, this variable SA. Okay, so we step in 1470 samples, and the frame length doesn't change, and this step is also determined using an equation which you'll see in the code. Okay, and once we got our next input frame, we need to copy it to the output, and we do that in a way such that we look for peaks in the last 441 samples of the current output, so that's this region here, and the first 441 samples of the input. So let me just zoom in on those. So we look for the largest value in the last 441 samples of the current output, and the first 441 samples of the red input frame. And then the next step is to align those peaks. So the peaks are shown by these black dots. So we line them up, and then we need to combine these two waveforms together. And we do this using what's called a crossfade function. And a crossfade is basically just a blend of the two waveforms. So we blend the red waveform and the blue waveform together. And when I hit the spacebar, we're going to see that crossfaded function being created. And I'll zoom in a little bit more so it becomes a bit clearer. But the green waveform is our crossfaded or blended waveform, which is a blend of both the blue and the red. At the very start here, the green waveform is predominantly equal to the blue. And at the very end, the green waveform is predominantly the red waveform. And in the middle, it's a 50-50. So gradually it becomes more and more influenced by the red waveform as we go down along the samples. But at the very start, it's predominantly the blue. At the end, it's predominantly the red. And in the middle, it's a combination of both. So this is what's called a crossfade function, and it ensures that we don't get any clicks or pops in the signal as we're time scaling. So once we've done that, we've then combined the next input frame to the output. This becomes our current output. We jump on 2 steps into the waveform. We get our next input frame. That next input frame will be combined with our output. We'll find the peaks in the search range or search region of at the start of the input frame and the end of the output frame. We'll line them up. We will combine them using that crossfade function, which gradually blends the two together. We then can create our next output frame, grab our next input frame, which is 3 times SA, and gradually keep on following that process until we build up our synthesized output. And that process is just repeated until we get to the end of the input signal. And that's it. That's an example of a very simple timescale modification algorithm. There are many alternatives available. They all basically try to achieve the same thing. They all basically try to discard or repeat certain segments. They also need to then blend the segments together in a smooth fashion so that you do not get clicks or pops.